Newton's second law of motion states that a force is equal to the change in momentum per change in time, or force equals mass times velocity. In this lab, we wanted to test that theory by running two experiments. Well, two experiments, yes. One experiment in real life where we drop an object and let it fall across a known length, and then one where we compute computationally. And hopefully, if Newton's law of motion stands up, we would see that our computational graph of position per time and velocity per time is equal to the actual observed position per time and velocity per time of our IRL experiment. So for my graphs here are my graphs. This is without drag. So as you can see, I mean the velocity is going down at a steady rate, and position is like slowly getting more and more. It's decreasing, but it's slowly decreasing more and more because it's accelerating. It's accelerating by gravity. And if I go into my program right here, this is my drag. Um, the velocity times t squared. And so if I wanted to change this to account for drag, I would subtract b from this, my velocity vector. And then for the position vector, it's a little more complicated. So I'll go to my spreadsheets to kind of show that. So what I did basically was like the initial velocity, right? The velocity beforehand, and then I added the velocity constant, how much it's going down, minus the drag constant, which changes per time. So you see this one is times 0.02. So the drag constant, the velocity constant times the time squared, which gives us the drag. And so you subtract that, and that's how you get the new velocity to account for drag. And so here are my results. Once again, I had the same trouble last time. I couldn't get these two to be on the same graph. Mostly it's just because the axes aren't the same. You see, like this starts at 0, and then the y starts, and then it starts at 0, then goes to 1, whereas like this position like starts at 1, goes to 0, and you can see that effect on the graph. But if we zoom in for a little bit, you can see that my position with gravity and position with gravity and drag, you can see that the drag makes it so that it takes like just a little bit longer for the object to hit the ground or hit 0. And if we actually, I know it's not perfect, but if you actually like kind of put this over, you can see that it's more closely associated with the one accounting for drag, which yes, of course, that makes sense. It's more applicable to the real world. And then if we go to velocity, the velocity is kind of the acceleration is decreasing, so the velocity, it's still going down but at a decreasing rate with the drag, whereas without drag, it's just constant. And my velocity for my tracker kind of messed up, so ignore that. Yeah, terminal velocity. Okay, yeah, terminal velocity. Okay. Um, are my graphs? So my graphs don't show terminal velocity, um, but you can see that, like, you can see with the velocity that this is slowing down. So eventually, it would get to the point. It would reach the point of terminal velocity, and at that point, the object is no longer accelerating. Therefore, the net force in the object is 0. Um, And then for the second what if the object was thrown down, that really wouldn't really change anything unless we were able to, throw it down, like, I guess past the velocity, that would be terminal. But I doubt we could do that. It wouldn't change anything. It's just instead of starting at 0 velocity, depending on how hard we threw it, it would start like somewhere around here. And then, the change in velocity would follow the same trajectory. So no, throwing the object down wouldn't change the terminal velocity.